Alright, so I'm doing a homework problem here, mostly because it makes just more sense to me study-wise to go through a video and talk it out. So that's kind of my main reason, but I mean, I guess if other people get use out of it, then that's even better. Um, so this was a homework question that we had, and I also want to say that I am not entirely sure if this stuff is all right. I'm doing what I think makes sense. After studying it, but I'm not 100% as I 100% sure of how to do all these. So this one is a capacitance question. And we have these three long cylinder conductors with these radii A, B, and C, and they're connected in series. The outer surface of conductor A and B have a charge of plus Q. Unit length an inner surface conductor B has negative Q. Now it wants us to find the capacitance per unit length between shell A and B. So capacitance is defined as our charge Q over our potential V. So if we have our potential, we're good to go here. And the way that I would find potential, find V by finding our electric field. Okay, and that's because your potential is the negative integral of our E field. So I'm going to start by just putting the picture down over here, and we'll find the E field using Gauss's law because of the cylindrical symmetry we have here. And then once we have the E field, we can find the potential. And then once we have the potential, we can find the capacitance. Okay, so I'm just making this picture a little bit bigger here. Okay, so I'm going to draw a little Gaussian surface between A and B, which is the first region they want us to find the potential. Obviously, this is not my best work, but it's fine. As long as we get our surface here, and we'll call it a surface of radius r. Okay, so we can use Gauss's law to get the E field pretty easily here because of the symmetry. So Gauss's law says the closed surface integral of our electric field dotted with dA is equal to our enclosed charge over epsilon naught. And the integral on the left-hand side, we've done this before. It's going to be the magnitude of E times our dA, which is 2 pi LR. Now, if we think about the charge enclosed inside our Gaussian surface, it's just this plus Q. So a lot of times it takes a little bit of work to find the Q enclosed, but it's actually pretty easy here. So very easily we can find that your E field is equal to Q over 2 pi L epsilon naught R. And that's in the R hat direction. Now if we want to find our potential, well, again, potential is the negative integral of our E field. Good night. So we have our E field, that's why we found it. We can put it in here and find our potential. So our potential is negative the integral Q over 2 pi L epsilon naught R. And then our DL is going to be just R hat dr. So R hat is just 1, so we'll be left with just dr. As for our limits of integration, we're going to be going from B to A. From B to A. Okay? So B to A. So in the next step, I'm going to pull out constants, and I'm also going to flip my bounds of integration and go from A to B. Well, before I do that, let me pull out my constants. Q doesn't change. That's just the charge. 2 pi L epsilon naught constants. the integral from a to b of 1 over r dr. And this is a pretty easy integral to do. We'll know that that's just the natural log of b over a. So then our potential is q over 2 pi L epsilon naught, the natural log of b divided by a. Okay. All right, so we have our potential, and then we need to find our capacitance. So capacitance is going to be q over our potential. So if you were to plug that in there, you'll have q over q, natural log of b over a, over 2 pi L epsilon naught. So you can see the q's drop, and our capacitance is then 2 pi L epsilon naught over the natural log of b over a. And just the way the question's worded, and I noticed a lot of questions are worded this way, maybe that's a thing, it's the capacitance per unit length. So for that, we want C over L, and your L just goes away. So you get 2 pi epsilon naught over ln b over a. That's our capacitance per unit length of that first bit. Now for part B, well, let me just draw a new Gaussian surface so we can see. Part B actually will be pretty easy. We won't have to do much work, thankfully. So for part B, we want to go from between B and C. So our Gaussian surface would be somewhere in this region. And we'll give it radius r still. Okay. So now if we think about what the charge enclosed is, we have a plus q, a minus q, and a plus q. So that will leave us with just a charge density q. Or not charge density, charge enclosed of q. So when we do our Gauss's law again, so it's the exact same step. We need to find our E field over epsilon naught. And we get still E times 2 pi LR is equal to Q over epsilon naught. And yeah, this is pretty much the same thing as before. Nothing really different here. You'll get that your E field okay, cool. Just making sure I use my vector notation right. Your E field is still going to be Q over 2 pi L epsilon naught R in the r hat direction. The only difference is when we integrate, so we have the same E field. When we integrate our E field, so when we do the same integral, it's going to be the same integral. The only difference is instead of going from B to A, it'll be C to B. So that's the only difference in this problem, is we're going from here to here. So I'm just going to go ahead and write down what I get for that. I get Q over 2 pi L epsilon naught. That's just as before. This is the only difference. You'll get the natural log of C over B now. And if you want to find your capacitance per unit length, well, you'll see that that's going to be pretty much the exact same thing. You'll get 2 pi epsilon naught over the natural log of C divided by B. Okay, so that is part B. I guess I technically did part D first, and that is Well, part C wants us to do the same thing from A to C. And then D wants us to find a general formula for the addition of capacitors. I did D first just because I think we can see what's happening here. So by superposition, if we want to find the potential from C to A, that's equal to the potential from B to A plus the potential from C to B. All right? So, and capacitance is again Q over V, and V is Q over C. So if we want to know something about our capacitance, we can use our superposition here and here, and we're good. So in our case, we'll have V from C to A is equal to, well, we already have it there, so I'm just going to rewrite this in terms of our capacitance. Q over our capacitance from C to A equals Q, our capacitance from B to A before C to A, plus Q over the capacitance C to B. And the Q, they all have charge Q. That doesn't change, right? So then we get 1 over capacitance C from C to A is 1 over the capacitance from B to A plus 1 over the capacitance from C to B. Well, we already know this, and we know this. So if we find it, add them together. Well, we already found it. If we add them together and we invert it, we can get our capacitance C to A, which gets us 2 pi epsilon naught over the natural log from A to C. Okay? So that is that part, and I just kind of use the general equation to get it, but this is, if you want to find just in general, then your total capacitance is 1 over C1 plus 1 over C2 plus ... plus 1 over Cn. So you could say that your capacitance is equal to 1 over the summation of 1 over C sub I, where I starts at 1 and goes to n. This is, I guess you could say, a general rule, and then this is what you get. Which hopefully, I think we've seen that before in physics too when we work with circuits, capacitors in series. That's kind of what you do with those. So yeah, that was kind of how I approached this problem, and I feel like it makes sense to me, and hopefully it helps other people too.